the other way that we can do certain types of understanding what's going on in the brain is with what's called physiological measurements. And so again, using animals, typically what you'll have is you have a screen where certain things are being displayed, an animal whose head is restrained so it's looking in a particular direction, and there's actually an electrode recording from the neurons in the brain. You hook that up to an amplifier. In the old days, you'd look at it on an oscilloscope, and actually you would just connect it to a speaker and you'd listen. And more clicks meant you were getting more response, and you'd have to write it down and report it. Then you had an oscilloscope that had traces. Now, of course, it's all computerized. All right. You've seen this picture before. This is a picture of what it looks like for a microelectrode to be recording from a neuron. And up on top, this is what the actual voltages look like, these spikes. And so then down here, you have something that just sort of counts the spikes that go across. So one of the first areas that people want to look is what was called V1. Back in the old days, it was actually called Area 17, I think, but that sounded too much like UFOs or something. I don't know. It's V1, the first visual area. And when you record from the first visual area, and here's an example, the way you get a monkey to look in a particular place is you give him juice whenever he pushes a button when something happens, and so he'll attend very carefully there, and it happens, he pushes the right button, he gets juice, and apparently monkeys really like apple juice. But while you're doing that, you're doing other things to the visual field. And one of the things they've found is that there are cells that if you put up a bar, if you put the bar, let's say, horizontally, you get hardly any reaction at all. In fact, put it up at a 45 degree, still hardly any reaction. Put it up vertically in this case, and you get a tremendous amount. And by the way, again, this is the part where it's off, this is the part where it's on, this is the part where it's off. Now, for this particular trace, I don't know if the bar was moving at all or just being flashed up there. The movement I'll show you in just a minute. But the idea is that within V1, the first visual area of cortex, there are cells that are extremely sensitive to the orientation of essentially edges. Remember we did oriented edge detection? So this feels an awful lot like oriented edge detection. It would be an oversimplification to say that's what it's doing, but it's related. If you recall, we also talked about motion. Well, it turns out in V1, you also get directional selectivity, all right? So here we have a cell, and these, of course, are the spike trains. And this particular cell, if you have a bar that's tilted a little bit and moving upwards, you get a small amount of motion. If you have a bar that's here on this 45-degree angle and you moved it upwards, you got a lot of spikes. What's remarkable is when you move it down, you got no spikes at all, or even less than resting state spikes. So not only do we have orientation selectivity, we have movement selectivity. And you can actually make a pretty cool plot of how this distributes in the brain. And so this is essentially, I guess this is your brain on drugs, because, I don't know, anyway, it's all colored. But the idea is that each of these colors represents these different orientations, and you can get these mappings, and you can see that it's not randomly scattered individual points. There are regions, all right? And in fact, these are referred to as hypercolumns in the sense of that little tissue areas within the brain will all be associated with a particular movement. Now, remember, it was retinatopic, so this area is all from one part of the retina. Sure, but within that area, there'll be little subparts that are for verticals and oriented edges like that, including different kinds of motion. So those were the kinds of things that people saw in these first visual areas. There was a group of neurophysiologists, Hubel and Wiesel at Harvard, who I think did work in cats originally, where they first looked at these, some of these cells. They also looked at things called XY cells having a steady state in motion, and they won the Nobel Prize for this work. Okay, so this idea of trying to understand how the visual cortex was processing the visual signal was really, in fact, that Nobel Prize was announced during when I was in grad school, so it was in the 80s at some point. So that gives you an idea of sort of the recency of some of this work.